Hi, D101 and D102. I think I figured out the dreaded 15D problem from the homework, and instead of just kind of writing it out on a piece of paper and emailing that out, I thought I'd do it on the whiteboard with us so you guys can kind of watch and follow along. So to start, let's remember the three marginal probabilities that we're dealing with. We have a total of 20 marbles. We have our red marbles, which we have a 7 in 20 chance of drawing on any particular draw. If we just solve that out, that comes to a 0.35 probability of drawing a red. We also have our blue marbles, which we have an 8 in 20 chance of drawing on any given draw, so that'll be a 0.4 probability or 0.40. And then we also have our green marbles, which there's only 5 of those, so 5 divided by 20 for our green marginal is going to be 0.25. So these are our marginals we're dealing with. 0.35 for red, 0.4 for blue, 0.25 for green. Now, just like we did with the dice problem, or you can do with like coin flip problems, we can figure out how many possibilities we have if we're drawing one marble 3 different times, or one marble over 3 draws. So a little trick you can use is if you have 3 possibilities, you can start there, and you want to know how many possibilities there are over multiple instances, like say multiple flips of a coin or multiple rolls of a die, you can actually raise your 3 probabilities to the power of however many instances you're going to do. So we have either a red, blue, or green. We have 3 instances in which we're going to draw. So we're going to have 27 total possibilities. So 27 total combinations of different marbles we can draw. So with that in mind, we have 3 marbles, 3 different kinds of marbles, 27 possibilities. That's going to be 9 for each marble first. There's a truck driving by. Anyways, so let's just map that out. We'll do 9 draws that start with a red, 9 draws that start with a green, and then 9 draws that start with a blue. So I have 9 draws that start with red. Nine that start with blue. And 9 that start with green. Okay, so we could draw 3 times and we could get a red, and a red. We could get a red, and a blue. We could get a red, and a green. We could get a red, blue, blue, red, blue, green, red, blue, red. We could get a red, green, green, a red, green, blue, and a red, green, red. So we can just go ahead and like fill out the rest of these in that same way, right? So blue, 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 green, blue, blue, red, blue, red, red, blue, red, green, blue, red, blue, blue, green, green, blue, green, red, blue, green, blue. We can do green, 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 red, green, green, blue, green, red, red, green, red, green, red, blue. We can do green, where am I at here? Blue, blue, green, blue, red, green, blue, green. So these are 27 different possibilities for 3 independent draws, right? And so what we want to do now is, our question is at least 2 red, and it doesn't matter where their draws are. We want to find the instances in which we have at least 2 red. So some that are immediately obvious, we have this here, that there, going down, there's one, there's one, there's one, and there's one. Yeah, so that gives us a total of 7 different instances in which we might draw 2 red marbles over 3 draws. So now all we have to do is find the probabilities of each combination of draws, right? So each draw is going to be independent. So the draw of a red with replacement times the draw of a red with replacement times the draw of a red. Those 3 things are independent events, the draws are. Therefore, we can use our multiplication rule. So if we do red, 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 that's 0.35 times 0.35 times 0.35. We get 0.043. And if we go through and do this with the rest of them, red, red, blue, that's 0.35 times 0.35 times 0.4. 0.049. Note that I'm rounding to 3 columns. Red, red, green, 0.35 times 0.35 times 0.25. That's going to be 0.031. And then just continue on doing that. Remember, all 7 of these combinations are going to be combinations of 3 independent events, so we just do the multiplication rule there. They're joint probabilities for independent events. So I'm just going to go through and fill out the rest of these. So we got red, blue, red, that's 0.049. We got red, green, red, 0.031. We got blue, red, red, 0.049. And we got green, red, red, 0.031. Okay, so now we want to figure out what the total probability for all of these possible combinations of 3 would be, given we have 7 instances in which we have at least 2 reds. We treated the draws as independent events, so one draw is independent of the next draw is independent of the next draw. However, the combination of 3 are going to be mutually exclusive, right? If I draw 3 reds, it's impossible that I also drew a red, red, and a blue. Just like it's impossible that I'm in Canada and the United States at the same time. So, because these are mutually exclusive, and we want to know what's the probability of either getting 3 or getting that combination or getting that combination, that is, because they're mutually exclusive and now we're interested in a union, we can just add all these up. So we could use our addition rule. So essentially, to just kind of repeat, what we're asking ourselves is, what's the probability of getting this, or this, or this, or this, or this, or this, or this? Because any one of them will satisfy the at least 2 red marbles, right? So we can just add all those up. So let's see, we have 0.043, 0.049, 0.031, 0.049, 0.031, 0.049, 0.031. If we sum all those up, you should get somewhere in the ballpark of 0.283. So the probability of getting at least 2 red marbles on 3 draws here is about 0.283. And I believe that's the answer to 15D. If there's any other issues or if anyone got something different and feels pretty adamant about it, feel free to shoot me an email. I'll look it over, and if it's compelling enough, I'll send out a correction or something like that. Otherwise, I hope you all do well with this. I hope you all do really well in your midterm, and good luck, and I'll see you all on Tuesday.